Okay. Good afternoon, good morning, everyone. I'm very glad to have the opportunity to share our achievements with you. My topic is research on water supply scheme of emergency groundwater source based on a simulation and optimization model. I come from Nanjing Center, China Geology Survey. Okay, my report includes the 5 parts: introduction, study area, methodology, results and discussion and conclusions. Okay, introduction. First part is introduction. Okay, as we know, affected by global climate change and human factors, a serious problem of water source has emerged all over the world. Water, such as water scarcity, water pollution, and droughts. In response to the sudden increase of natural or man-made disasters in recent decades, the UNESCO International Hydrogeological Project undertaken the Groundwater for Emergency Situations project and provided the methodological guidance for the groundwater as emergency water source. Okay, in my topic, I researched the study area is Nanchang. Nanchang is situated in the north central part of Jiangxi province. The annual plain of the lower reaches of Ganjiang River or Fuhe River. In recent years, season water shortage events often occur in Nanchang, which threaten the safety of water quality in Nanchang. We can see from the picture that a man jumps across the almost dry ditch along the cracked river bank of Ganjiang River in Nanchang, December 3, 2007 year. Another picture shows us similar conditions. People walk on the riverbed of Ganjiang River, a tributary of the Yangtze River in Nanchang, capital of the East China Jiangxi province, October 14, 2019. The water level of Ganjiang River in the Nanchang section fell to 11.57 meters due to the next rainfall. Average precipitation in the province stood at 96 from the late July to early October, and about 17% less than the average in the previous years. So we should analyze why the city, the water supply system unreasonable. In fact, the source of water supply in Nanjing City is relatively single. Urban water supply mainly depend on the surface water, Ganjiang River, and accounts for 96% of the total water consumptions. We can see from the figure that the precipitation is unevenly distributed throughout this year. Moreover, the precipitation varies greatly within years. Okay, the study area. The study area is located in the plain area of the lower reaches of Ganjiang and Fuhe River. The magnitude and the latitude. The study area of the north side is the south branch of the Ganjiang River. The west side is Aixihu Lake. East side Yaohu Lake, and the south side is the river. The contrary is widely distributed in the area with a thickness 20 to 30 meters. The groundwater is mainly loose pore water. Most aquifers are of binary structure. The lower side of soil is the main aquifer with a thickness of 10 to 20 meters and has abundance of water. The comprehensive permeability coefficient of aquifer is about 80 to 120 meters per day. The depth of groundwater level is about 9 to 50 meters, and the water level changes by 3 to 5 meters. Okay, methodology, hydrogeological conception model. In this work, we set the boundary condition into two categories. The north side is the Kirsten head, and the east side and the south side is the general head boundary. Flow simulation model. In this work, we use the model flow to simulate the groundwater flow. A model flow is a block-centered finite difference code that simulates saturated flow in 2 or 3 dimensions with varieties of boundary conditions. The automated inverse model code, PAST. Okay, spatial and temporal discretizations. Okay, the model everywhere was discreted into horizontal grid of 350 rows and 258 columns with a cluster spacing of 50 meters. The top and bottom elevation of the layer for each model cell will computed based on the digitized tomographical map and thickness contour maps. Okay, there's the model simulated transient pumping time from 2017 to 2019. And the each stress period was divided into 12 time steps. Water level data for January 2017 were used in as the initial head values in the model. Okay, we used the initial values of soil properties. These data were obtained from a variety sources, including pumping test, the soil test, and the literatures. The model domain was divided into 14 zones for the parameterization that includes hydraulic conductivity and the recharge. The model calibrations. Okay, for this study, we automatic parameter estimation code PAST was used to adjust hydraulic parameter values until the best fit was obtained between the observed and simulated or measured water levels. Okay, from the figures, we can see that there's a good agreement between the observed and the computer values. That means we use the measure values and the computed values to comparison to calibration the CPG field and the groundwater level. Okay. Linkage between simulation model and a G-based optimization model. In this work, we adopt the genetic algorithm to link the simulation model. To update the state variables hydraulic heads in the optimization model, the calibrated groundwater flow model, which is based on the model flow and linked external with the GA optimization. The roadmap, the figure is the roadmap, how to capture the GA algorithm and the simulation model. The optimization model, we set up the object function of the model and showing the following. The Drilling represents the construction cost of the single well. Inactive represents the number of pumping wells. The NOBS represents the number of the observation wells. And Z represents the total cost of the construction well. Okay, use a calibrated model. We use the model to optimize the single well pumping rate, the pumping number of the pumping wells, and the scheme 3, the location of the pumping wells. Scheme 1, constraint conditions include pumping rate of single well, the total water supply, and the aquifer. We can find the thickness of the aquifer be dewatered from 15.9 to 13.24 meters. The average drawdown funnel from 15.98 kilometer square to 14.5, and the groundwater level recover from 94.84% to 95.55%. The figure shows the seepage, failed compression, and the groundwater level recover under different ground pumping schemes. Yeah. Similarly, we use a model simulated under the scheme 2. Construction conclusion includes the pumping rate of single well, total water supply. The aquifer is not okay. It's similar with the upper similar with the scheme 1. Okay, scheme 3. Constraint condition is more includes the distance of pumping well less than 200 meters. That includes the location of the pumping well. Finally, we use the model to simulate it under the target, the water supply target. The figures show the different schemes, the pumping well layout. Conclusions: optimization of the pumping rate of single well, the number of pumping well, and the location of the pumping well. The cost of groundwater extraction has been reduced by 4.92% and 50.67% and 42.35% respectively. Simulation and optimization model can not only simulate the complex groundwater flow system, but also obtain an optimal exploitation scheme by satisfying the objective functions and constraints, and which is an effective tool to solve the problem of groundwater management. Okay, that's all. Thank you everyone.